nanohub.org. Online simulation and more for nanotechnology.
Then Neda Habibi. She was formerly at the Alamo Colleges. She was at Northwest Vista College, and she just started at her new university. And then University of North Texas. Did I get that right this time? Very good.
Correct. So I'm Neda Habibi. I'm an assistant professor at University of North Texas, and also I'm a co-PI with the National Mentech Micro-Nanotechnology Education Center. So today I will be talking about FTIR and UV visible spectroscopy techniques. So we're going to talk about an introduction to FTIR. I'm going to talk about theory of FTIR, working operation of FTIR. We're going to talk about types of vibration, the instrument, and then I'm going to talk about UV visible spectroscopy and why we use UV visible spectroscopy and what kind of information we can get from both of these spectroscopy techniques. So in general, spectroscopy is a science of studying the interaction between a radiation and material. So we can have different types of radiation and different types of electromagnetic waves. And depending on what type of radiation we use, we can get a set of information. And also it depends on the material, depends on the radiation and electromagnetic waves that we are using. They will interact differently with the material. So we will have a set of information and we can use that for characterizing, getting some data about our material and about the component of the structure we have. So in Fourier transform infrared spectroscopy, the radiation and electromagnetic wave that we have is in the range of infrared spectrum. So FTIR spectroscopy is a molecular spectroscopy, which we use it for characterizing both organic and inorganic material. So actually, FTIR is a widely used technique. It can be used by chemists, physicists. If you're a material engineer, you can use FTIR for characterizing your material. So it's a widely used technique, and a lot of labs, they have FTIR as a characterization tool. So in FTIR, the type of radiation is in the range of infrared. We have electromagnetic waves in the range of infrared. And the sample is bombarded with infrared radiation. And when the frequency, specific frequency of that infrared matches the natural frequency of those bonding in specific material, they will actually absorb that frequency and they will start to oscillate. And this is very similar to oscillation of a spring. And we have some vibration. So some portion of that infrared wavelength is absorbed by that material. So as a result, we have a chart, which we have transmittance versus wave number. So the output, the result is a chart. And the information that we can analyze is actually information about the bondings, chemical bondings, whether we have, for example, carbon-carbon bonds, carbon-oxygen bonds, and so on. So radiation electromagnetic spectrum is where we have electric and magnetic field oscillating in single planes in the right angle from each other. Electromagnetic radiation is the energy propagated through a free space or through a medium or through our material interacting with that material. And as a result, we have a peak signal that we can characterize our structure, our material. And depending on what type of radiation we use, we have a set of information. As you can see in this picture, we have very short wavelengths, which are gamma, X-ray. As we go to longer, we have ultraviolet UV, and then we have the visible range. So the infrared is beyond the red visible range of our electromagnetic spectrum. As we go forward, we have, of course, longer wavelengths and less frequency. So the IR radiation is the wavelengths longer than the red end of the visible light and shorter than the microwave. So they are between the red and microwave region. Roughly between 1 to 100 microns is the wavelengths. And actually our skin emits infrared, a source of heat that has infrared light, so it can be captured by night vision goggles, and that's how we can see objects and people in night with night vision goggles. So the material that you use for testing, as I said, FTIR is used by chemists, it's used by physicists. So the material is also a wide range of materials can be used for testing with FTIR. If you're a chemist, your material could be like polymers, drugs, paints, pigments. If you're a nanotechnologist, your test sample could be like powders, nanomaterials. And also you can use FTIR for characterizing thin films. So a wide range of materials can be used for testing with FTIR. And the information that we get is information about the chemical bonds that are existing in that structure. So interaction of radiation or IR with our material, depending on their molecular system, they will absorb energy in discrete amounts of level, like in specific frequency, which is depending on what bonds they have. And the molecular system of material, it includes like certain discrete energy values. So it will also absorb energy in specific frequency and in discrete amount of levels. As a result of absorbing that IR radiation, that molecule will vibrate and have a motion. Is very similar to oscillation of a spring, and absorbing that energy will cause the molecules to vibrate, and we will have a peak or signal that we can refer those peaks to specific bondings and kind of have an information of what type of bondings are existing in our specific material or test sample. So as a result of interaction of IR with the bondings, we have vibration of those bondings. So there are two main categories of vibration, which is stretching and bending. Stretching is changing in the interatomic distance between the atoms with respect to each other. Stretching can be symmetrical or anti-symmetrical. In symmetrical, both atoms at the same time are going away from the central atoms and coming back. In the anti-symmetrical, one atom is going away from the central atom and one atom is going near, so it's anti-symmetrical. In the bending, we have change in the bending vibration. We have change in the angles between the atoms. And four types of bending vibrations are scissoring, rocking, twisting, and wagging. And scissoring is an in-plane vibration, which both atoms are coming towards each other, like a scissor motion, and going far is an in-plane vibration. In rocking, it's like a rocking motion. Atoms are rocking in clockwise or anti-clockwise motion. And also twisting and wagging. In wagging, both atoms are going like towards us and going away. So it's an out of plane vibration. And twisting, one atom is coming towards us, one atom is going far. So it's kind of having an out of plane vibration. This is all a result of these bondings absorbing the IR electromagnetic waves and IR radiation. We also have the rotational motion, which is a tumbling motion, also a result of absorbing IR radiation. We have a tumbling motion of these atoms. It's very similar to having like an oscillation of a spring. That will also cause a peak, absorbing that IR in specific frequencies that we can see in the chart of FTIR. So the resulting information that we get from FTIR is a chart where we have transmittance versus wave number. And so all of these specific frequencies, specific peaks that are indicating absorption of a specific frequency from the bonds of that material. And from the positions of these specific peaks, we can correlate them to specific bonds and kind of guess what types of bonding, like carbon-hydrogen, carbon-carbon, carbon-oxygen, different types of bond, whether it's a single bond, double bond, triple bond, and so on, depending on the position, because each bond will absorb those IR radiation in a specific frequency. And transmittance is, so once that bond is kind of absorbing a fraction of that IR radiation, so we're not having like 100% transmittance. So in that area, we have a peak that we can recognize and analyze. So we have different four regions of a chart. The first region, which is from like 500 to 1500 centimeter power minus 1, which is the wave number, is the fingerprint region. And actually in this region is a complicated series of stretching and bending vibration, and is more difficult to correlate peaks to like specific bonds. It's more difficult to analyze peaks in the fingerprint region, which is the red one. And after that, we have the functional region, or it can be called the diagnostic region. And we can more accurately correspond a peak to a specific bond. We have the yellow part, which is the double bonds. Blue is the triple bond. And then we have single bond stretching. And depending on specific frequency and the position of the peak, we can correlate them to like specific bondings, and kind of guessing what functional groups or what bondings we have in our sample. So the fingerprint region, which is the region to the right-hand side of the diagram, is about from 500 centimeter power minus 1 to about like 1500 is called the fingerprint. Usually contains a complicated series of absorption, and it's more difficult to analyze the peaks in the fingerprint region. So the properties of the peak, we have intensity. It could be like a weak or strong peak. It's the shape. It could be like broad or sharp. And most importantly is the position in the diagram, which we can correlate the specific frequency of the IR radiation with specific bondings in a structure. So some definitions of wavelength is actually the distance between 2 points, the start point and the end point of one wave, one particular wave, and the wave number, which is the number of waves that are fitting in a unit of distance. So the unit of wave number is 1 per distance, or like distance power minus 1. So for example, 500 centimeter power minus 1, in 1 centimeter we have 500 waves. So in the diagram, we have transmittance versus wave number in the FTIR chart. So working operation of FTIR, sorry, this is FTIR. FTIR is used to analyze functional groups and chemical bondings in a molecule. In FTIR, electromagnetic waves in the frequency range of IR is exposed, bombarded to a sample. Based on the certain molecular bonding, that molecule will absorb energy in specific frequency. The absorbed energy will cause the bonds to stretch, vibrate, or rotate. And the stretching vibration is kind of similar to spring oscillation. So as the matter is absorbing energy in those wavelengths, at certain frequencies, the transmittance of the wavelength will be less than 100%, and that is where we have a peak in certain positions. Those peaks on the FTIR chart can be corresponded to specific bondings and functional groups, and is therefore used to analyze the chemical bondings of a material. So another spectroscopy technique is ultraviolet, UV, and visible spectroscopy. This is actually one of the most commonly used spectroscopy technique. I could say like in almost all kinds of like chemical labs, biology labs, we have a UV visible spectroscopy. So the radiation and electromagnetic waves that are using UV visible is actually in the range of visible and also ultraviolet electromagnetic waves. And so what information we can get with UV? And so with UV, we are shining electromagnetic waves in the range of UV and visible through a material. And those materials, depending on their energy levels, they will absorb a specific frequency of these wavelengths, and the electrons will get excited. They will go to higher level of energy. And so depending on the material, they are absorbing a specific frequency in UV and visible. So the how much they absorb that light is actually depending on the concentration of that molecule in the solution. As we have like a more concentrated sample, they absorb more of that light. So what we are having that light getting transmitted is less, and the instrument is kind of analyzing and measuring the transmittance and correlating that transmittance to absorption, and that absorption is related to the concentration of those molecules in the sample. So why we use UV visible spectroscopy? The kind of information that we can get with UV visible spectroscopy is analyzing the concentration of molecules in a solution. Also, we can analyze the maximum absorption wavelength. And so what is the maximum wavelength that this sample is absorbing? And we can kind of have a guess about the functional groups, but it's not an accurate method for detecting functional groups because we have a lot of functional groups and bondings that absorb UV and visible wavelengths in like the same frequencies. But we can kind of guess, have a guess about functional groups, but it's not a very accurate technique for guessing the chemical structures. For more accurate information, we can use like FTIR and so on. So the UV radiation, which is the wavelength range of UV, starts at the blue end of visible light and ends at almost 2000 angstrom. So that's where we have the UV radiation. So in a UV visible spectroscopy, we have like a source of light, and then we have a monochromator, which is diffracting light and diffracting light into all those individual beams. We can choose one individual beam in the range of visible and UV, and or have like a range of light shine to a sample. And then we have a beam splitter, which in one sample, which is a control sample, we have water, which water doesn't have any molecules that can absorb UV and visible. So if we have water, all the intensity that we are shining to that water will pass. So the initial intensity is equal to the intensity that is being passed from the sample. And then we have a sample cell, which we loaded with our sample solution, which, for example, contains like proteins, DNA, or any other molecule that is actually absorbing those frequency in the range of UV and visible. So once that material is absorbing, the amount of light that is transmitting through that sample is going to be less. So the instrument is actually measuring the transmittance of light and then correlating the transmittance to absorption to kind of have an idea of what absorption is this sample absorbing, what frequency the sample is absorbing, the maximum absorption, and also the concentration of the sample. So when a sample is exposed to light, when the energy level of electrons matches that specific frequency of UV and visible, they will absorb that light. Electrons will get excited, they will go to higher levels. And in UV visible spectrometer, we'll record the degree of absorption of the sample at different wavelengths and kind of correlate it to absorption values and correlate that to the maximum wavelength of absorption. So the chart that we get is absorbance versus wavelength. And this is two examples, two UV visible chart for like isoprene, and this is acetone. We can see that the maximum wavelength of absorption for isoprene is around 200 nanometer in the range of UV. So we can, this is an important information that we can get from UV, the maximum wavelength absorption for different material. So the significant features, information we get is the lambda max wavelength at which there is a maximum absorption in that wavelength, and the intensity of that max absorption. So once we get that intensity, we can correlate it to our unknown samples. Let's say we have samples that we want to know the concentration of these samples. So we can get some known samples, measure them with UV visible, and kind of have that intensity of absorption and correlate that absorption to an unknown concentration sample and kind of have a guess of what is the concentration of the unknown sample. So the instrument UV visible spectrometer actually measures the transmittance, which is initial intensity that is shined through the sample versus the intensity that is passing. Then the transmittance data is plotted to absorbance with the Lambert-Beer law, which indicates that the absorbance of light is directly proportional to the path length and the concentration of those absorbing species. So here you can see the Lambert law equation. A is the absorbance. Epsilon is the molar absorption coefficient, C is the molar concentration, and L is the path length, which is the path length of the cuvette that we use to kind of load our samples. You can see in this picture. So as I said, measurements with UV visible, we can have the intensity of absorbance plotted to concentration, and we can also have like briefly information on the chemical groups. For example, some hydrophobic benzene groups, they absorb UV ultraviolet light, so we can kind of have a guess of like functional groups and chemical bondings, but it will not be an accurate detection for chemical groups. So I'm just going to conclude it here.